Hi, I'm Mitch, and this is the second video in a series on magnification using a simple lens setup. And in the previous video, we developed this ray diagram and then associated with these two lens equations, showing that magnification is just image distance over object distance, and then relating focal length, object distance, and image distance with the lens equation. And this formula suggests that if we want to have a high magnification, we can achieve that with a very small object length, or less practically a very, very high image distance. But of course, there's practical limits on the object length as well, and you can't unilaterally change one of these without changing at least one of the others. And so what I'd like to do in this video is to maintain a constant focal length lens and then just move my object around relative to that lens and see what happens on the other side here. And so the first iteration of that would be to move the object closer, but still larger than the focal length, but less than 2 times the focal length. So you may remember that our original image distance was 13 millimeters, and so now I've moved it just a little bit closer to the lens focal length and made it 11 millimeters. And so now we begin to draw our two rays, the parallel ray and the ray that comes down through the center here. And you may notice that the angle between these two rays has gotten larger. So that means that these two rays are diverging more quickly. So if we just continue to draw those rays, now on the back side of the lens, they begin to converge, but they're converging a lot more slowly than they were before, which means that it takes them longer to converge. So we have a longer image length, and that results in a larger image height, H prime, and that means a greater magnification. So you can see that now the image length over the object length is 59 over 11, so we have 5.4 times magnification, whereas before we had something like 1.9, and we still have a real inverted magnified image. And as you slide this object closer and closer to the focal length, you will get more and more magnification, but this image length gets really, really long. So let's take that to its practical extreme and move our object to the focal length. So now we're going to have an object length equal to our focal length. So now you can see that our object is exactly on the focal length. The focal length was 10 millimeters, and now our object length is that. And we just start to draw our ray diagrams. And you can see that on the back side of the lens here, they end up parallel. And that means that our image distance becomes infinite. And now, because these two lines that started from the same point never converge, we don't really get any image. It's just a blurry image because you're sort of seeing the same point now in two different places, meeting your eye on the other side of the lens. But let's just keep moving that object closer and closer to the lens here. And so that means that now the object length is going to be smaller than the focal length. And you may remember in the previous video that I claimed that both object length and image length needed to be larger than the focal length for our real image to work out. And so you can see now, if we draw our ray diagram, our two rays diverge and they're never going to meet on this side of the lens. However, if you trace these rays back, you'll see that they do converge on this side of the lens. And what that creates is a virtual magnified image. And so it's a virtual image because the light doesn't actually go in this direction. However, if you had your eyeball on this side of the lens and you were looking through the lens, you would see an apparent image there, and it would be larger than the actual object, and it would appear to be slightly behind where the object actually is, and it's not inverted anymore. And if you had a camera or other detector on this side, that would see this virtual image as well. But the light rays aren't actually going there, and so that's why we call that a virtual image. And there's some other characteristics of virtual images that are worth looking into, but not in this current video. So that tells us what happens if our object length is less than our focal length. So now let's go in the other direction. Let's start again at our original object distance and move backwards. So you may remember that our original object distance was 13 millimeters, and so now I've moved it back to 18 millimeters, closer to 2 times the focal length, but still between f1 and 2 times f1. And you can kind of see that I've already given it away. If we draw our ray diagrams here, then my image distance becomes 23 millimeters. And so now if you work out that magnification, I over O, it becomes 1.3. So as we move our object back away from our lens, the image plane gets closer to the lens, but the total magnification decreases. So we're back to having a real inverted and magnified image here. And so let's just take this to its logical extreme. Let's take the object farther away to exactly 2 times the focal length. So you may remember the focal length was 10 millimeters, so 2 times f1 is 20 millimeters. If we draw our ray diagram, the image plane falls on exactly 2 times f2, which means that O is 20 and I is 20, which means our magnification is 20 over 20, or 1. And so now we have a real inverted image, but there's no magnification. So let's do one more iteration of this. Of course, I'm sure you can guess where I'm going. Let's take our object distance greater than 2 times the focal length. And I haven't even put a number on this because you can see immediately that O is the object distance is now greater than the image distance, and now our real image here is still inverted, but it's actually shrunken. It's not. It's actually smaller than the original object, and so now our image is getting smaller and smaller than the object as we move back.